Good day. This is the Professor, CBMG PhD. It's a Saturday, March 21st, 2026. It is 9:43 and 43 seconds p.m. Eastern Standard Time. And today's research, holography. So let's hop to it here. What we have then is incoherent radiation, a jumble of frequencies or colors, directions, and phases. Such light works well, but is almost worthless as a carrier of information. About the best that can be done with it is to turn it on and off in a sort of visual Morse code, which is exactly what is done on the blinker communication systems, sometimes used for ship-to-ship communication. It is of interest to note, however, that ordinary white light can be made coherent to some extent, but at a very high cost in the intensity of the light. For example, we might first pass the light through a series of filters, each of which would subtract some portion of the spectrum until only the desired wavelength came through. We would then have monochromatic one-color light, which is temporary coherent radiation, but it would still be spatially incoherent. The important thing about the laser is that, by its very nature, it produces coherent light automatically. So desirable are the qualities of coherent light that the complicated filtering process described above has actually been used. For example, one British experimenter used it in the 1940s in the attempt to make a better microscope, but so great was the effort and so meager the resulting light that this project was abandoned. In the course of the experiment, however, they did manage to make a special kind of picture using coherent light, which they called a hologram. They derived the name from two Greek words meaning a whole picture. Ordinary black and white photographs merely record darks and lights, or the intensity of the illumination, thereby providing a scale of grays, nothing more. But because waves of coherent light consistently maintain their relative spacing, they can be used to record additional information, namely, the distance from objects. It can be seen that the number of waves times the wavelength gives the precise distance to within one wavelength of light from the laser source to each object, but this would be a difficult process to implement. A better way, and one that is already in operation, is to use conventional methods to measure the approximate distance and use the laser beam for precise or fine measurement. The beam is split into two parts. One part is kept in the instrument itself to act as a reference. The other is aimed at a reflector which sends it back to a detector in the main device, where it is automatically compared with the reference beam. If the two beams are in phase, that is, if their crests are superimposed, the waves combine and produce a high-intensity beam at the detector. As the reflector moves closer to or farther away from the laser source, the beam intensity decreases, and then increases, again, as the wave crests move in and out of phase. The instrument counts the changes and displays the distance the reflector moves, as a function of the wavelengths on the control cabinet meters. Since the word for the interaction of the waves in a system like this is interference, the measurement process is called interferometry. Although not new, it can now be applied for the first time in machine tool applications, providing the accuracy needed in this age of space technology and microminiaturization. Measurements with a laser interferometer can be made with an accuracy of 0.5 part per million at distances up to 200 inches. Such precision was previously unheard of in a machine shop environment, having been limited to laboratory measurements and only at a range of a few inches. Under similar laboratory conditions, measurements by laser interferometry now detect movements of 10 to the power of 11 centimeter, a distance approaching the dimensions of an atomic nucleus. Now let us suppose we expand the laser beam and with the aid of a mirror direct part of it, the reference beam, at a photographic plate. The remaining portion of the diverging beam is used to illuminate the object to be photographed. Some of this light, the object beam, is reflected toward the plate and carries with it information about the object, as indicated by the wavy line, in the region where these two beams intersect. Interference occurs and a sample of this interference is recorded within the photographic emulsion. Where the two crests meet, a dark spot is recorded. Where the waves are out of phase, the process plate is clear. The result is a hologram, a complex pattern of fringes characteristic of the contour and light and dark areas of the object, as well as its distance from the plate. These fringes have the ability to diffract light rays. When light from a laser or a point source of white light is directed at the hologram from the same direction as the reference beam, part of the light is bent so that it appears to come from the place once occupied by the object. The result is a remarkably realistic three-dimensional image. There, in a nutshell, is the incredible new technique of holography. This strange kind of light provides us with yet other advantages. Indeed, one of the most important is the fact that the energy of the laser is not being sprayed out in all directions. All of it is concentrated in a narrow beam that emerges from the device, and it stays narrow. Laser light has already been shone on the moon, the beam spreading out to only a few miles and traveling there from Earth. The best optical searchlight beam would spread wider than the moon itself, thus dissipating its energy. It is for this reason, as well as its temporal coherence, that laser light is being considered for communications. A narrow beam is particularly important for space communications because of the long distances involved. But it is also possible to focus laser light as no light has ever been focused before. At close range, a laser beam can be focused down to a circle just a few wavelengths across, concentrating its energy and making it possible to drill holes only 0.0002 inch in diameter. Let us see what this focus ability means in terms of power. Consider by way of analogy a dainty 100-pound lady in a pair of spike-heeled shoes. As she takes a step, her weight will be concentrated on one of those heels. If the area of the heel is, say, 1/4 of a square inch, the pressure exerted on the poor tile or carpet rises to 400 pounds per square inch. And if the heel is only 1/4 inch on the side, the pressure will be 1,600 pounds per square inch. What we are getting at, of course, is the fact that the coherence of the laser beam permits it to be concentrated into a tiny area. Thus, whatever total energy is being sent out by the laser can be concentrated to the point where its effective energy is tremendous. The sun emits some 6,500 watts per square centimeter. Laser beams have already reached 500 million watts per square centimeter. But the power of the laser does not derive solely from its ability to be focused. Even an unfocused beam is several times more powerful than the sun's output per square centimeter. The crucial difference between the sun's light, or any ordinary kind of light, and laser light lies in the extent to which the emission of energy can be controlled. In the production of ordinary light, the atoms, as we know, emit spontaneously or in an uncontrolled fashion. But if the atoms can be forced to take in the proper amount of energy, store it, and release it when we wanted them to, we would have stimulated rather than spontaneous emission. This, however, is practically the same as the amplification principle we discussed earlier. In that case, a small radio signal is jacked up into a large one by stimulating an available power source to release its energy at the same wavelength and in step with the smaller signal. The question is, how can we do this with light? The laser and its parent, the maser, can be traced back half a century to its theoretical beginnings. The great physicist Albert Einstein is most widely known for his work in relativity, but he did early and important work on another gigantic 20th century scientific achievement, the quantum theory. In one of his papers published first in Zurich, Switzerland, in 1916, Einstein showed that controlled emission of light energy could be obtained from an atom under certain conditions. When an atom or molecule has somehow had its energy level raised, the release of this stored energy can be stimulated by subjecting the atom or molecule to a small shot of electromagnetic radiation of the proper frequency. Einstein wrote that when such a photon of energy caused an electron to drop from a higher to lower orbit, the electron would emit another photon of the same frequency and in the same direction as the one that hit it. In other words, The energy of emitted photon would be added to that of the photon that stimulated the emission in the first place. Here potentially was light, amplification, the three major factors: absorption of energy, spontaneous emission, and stimulated emission. Normally, more of the molecules in any substance are in low energy states than in high ones. They would change the natural balance and create a situation with an abnormally large number of high energy molecules. Then they would stimulate them to emit their energy by nudging them with microwaves. Here was amplification. They could even take some of the emitted radiation and feed it back into the device to stimulate additional molecules, thereby creating an oscillator. This feedback arrangement, they knew, could be carried out in a cavity which would resonate just like an organ pipe at the proper frequency. The resonator would be a box whose dimensions were comparable with the wavelength of the radiation, that is, a few centimeters on the side. On the back of an envelope they figured out some of the basic requirements. 3 years and many experiments. Later the maser microwave amplification by stimulated emission of radiation was a reality. The original maser was a small metal box into which excited ammonia molecules were added. When microwaves were beamed into the excited ammonia, the box emitted a pure, strong beam of high-frequency microwaves, far more temporarily coherent than any that had ever been achieved before. The output to an ammonia maser is stable to 1 part in 100 billion, making it an extremely accurate atomic clock. Moreover, the amplifying properties of masers have been found to be very useful for magnifying faint radio signals from space and for satellite communications. And this video was created for educational purposes only. My code name is Will. I'm Professor Christopher Brunet, leader of research, scientist, ufologist, psychic, computer technician, computer programmer, philanthropist, writer, mathematician, artist, photographer, film producer, chef, animal, and nature lover. My passion is world peace. Have a great day. Good day. This is